Hello, everybody. Um, while maybe people connect, I will explain what we are doing here for a moment and kind of tell you what's going to be happening today. So we are doing a series of webinars on creating our own little toy programming language. And today, this is part 2. It's going to be about grammars and like how they work, what they are, and why we need them. And the next time, we are going to start kind of looking at the implementation of the thing. And we'll start from the lexer. Last time I explained kind of different parts of a interpreter or a compiler of a programming language, which we need in order to create something like an interpreter. Okay, so during this talk, if you have any questions, please put them into chat in Zoom, and I will read them. Maybe I'll make a pause in the middle of this event, and for sure I'll do that at the end. Okay, so I think let us begin then. So grammars. What are to understand what grammars are and why they're needed, we need to first look at what a language is, believe it or not. So that's English, right? And you'll know this little phrase which is used to check how your fonts look. Okay, and this is a sentence in English. And this is also a sentence in a language, which is not exactly like something people use, but this is a language still nonetheless. And like when we use a language which we know, like English or whatever language you speak, we do not kind of even try to formalize anything, or it just happens naturally. But for a machine, unless it's an LLM or something, for a machine, it has no notion of language, so we need to explain to it what we want from it. And if we look at our English sentence and kind of pick out important parts of it, well, it kind of looks like this. So we have some kind of noun, some kind of action or verb, and another noun. And that's not too much really different from what we have like down there, because we can do absolutely the same thing here. So, of course, in that second case of the arithmetic expression, we have a binary here, it's a plus, and it has two operands, left and right. And they look kind of similar. And the point I'm trying to make here is that every language can be formalized in some way or another. And in order to formalize it, this is where we have grammars. If we go back a little bit and look again at our English sentence here, and we look at like those parts which were highlighted on the previous slide, we will have those three essential parts, which many languages, not all, but many, in a sentence formed according to all the rules and expectations, like the ideal sentence, they will all have, and they will have those in a specific order. So in case of English, we've got this. So we have like a subject, something that performs an action, the verb, the action itself, and an object, the thing over which an action is being performed. And this is a sentence. So it's by default in English, a sentence needs a subject, verb, and object, and nothing else really, because the other things are kind of a fluff. We can call them attributes or something, something of that nature. They modify and clarify the meaning of those three things. And sentences, when you string them together, they form a paragraph. Paragraphs form some text, and this is basically how we can describe like our normal everyday language. Of course, it's more complex than that, because whatever humans use, it's loosely formalized, let's call it that. Because you can have incomplete sentences, you can have like the word order reversed or mixed up, and so on and so forth. And for us it works, but for a machine like us, since we are creating a language of our own, it's much more constrained, the way the things you can do with a programming language. Okay, and so let's look at what grammars are. Well, formally, if we go full math, a grammar is that, what you see here. It is a set of non-terminal symbols, and I will explain what those are as we go. Terminal symbols, production roles, and a starting symbol, the way where the entire thing begins. And it's like a tree. So you start from this starting symbol, and it depends on symbols of the next order, and so on and so forth. And at the very bottom of the tree, you have those terminals. Okay, so let's see how it works out, really. Because, well, math is like good, I guess, but it's not something usually tangible. And I think well, at least I'm like that. I like doing things in practice and learning from practice, and not like starting from too much of theory, because this all is a formal theory. Noam Chomsky came up with those formal grammars, and we use them today for like in computer science and for parsing. But looking at this abstraction is not really, doesn't really tell us much. And like if you heard people like when they learn that you are a programmer, they say, oh, you must be good at math. Well, not really. I think programming is mostly linguistics, because it's about understanding and using languages. So, okay, enough of that. Let's go and look into grammars. And we'll start, of course, with our machine language, which is we will define a simple one here. And as we go, it will become more and more complex. So this expression here, as I said before, you have non-terminal rule symbols, terminal symbols, and production rules. And in this case, a production rule is something that describes our binary expression. So it's 42 plus 10. Let's just pretend that we only have 42, 10, and we can only plus them together. Okay. So this one, it's a non-terminal symbol, this sum rule thing. Why it is called non-terminal? Well, because it is defined through other things from our grammar. It will be more clear a bit down the line, but let's say that a non-terminal symbol is a symbol which depends on other symbols. So it's defined in terms of something else. And this, like 42 plus and 10, those are terminals because they are not defined in terms of anything else in our grammar. They are just defined by their string kind of representation. So terminals do not depend on other symbols, and non-terminals do depend on other symbols. And by the way, there are different ways of writing this grammar. But what I find helpful is this plain English kind of style. It is also adopted in the C++ standard. Its grammar is written in plain English. You won't find complex math symbols or anything there. So it's easy to read for a human. Okay, so, but if we look at that, that's not really good enough, is it? Because like, what, do we have like unique entities named 42 and 10? Well, of course we don't. We need to generalize them, make them more, well, kind of more generic. So kind of like giving them the common name. So what we are going to do is say that instead of 42 and 10, we have a number. And a number is either 42 or 10. So here we have number, which is a terminal symbol, because it only depends on some values, like some raw input. And this sum rule thing, which we have, it is a non-terminal because it is defined in terms of number. Okay, but again, what we could operate by numbers, of course, and only use the plus sign to add numbers together. But in order to make our grammar extensible, we need to separate this number thing into some other entity, which we can then extend. Like if we have numbers, we can also have like variables and so on. So our number, we will call it a literal expression. And now our sum rules will be literal expression plus literal expression. Literal is, well, what is literally written. People also sometimes call it a constant, like in your code. Numbers, character, well, character values, chars. What else? I don't know, strings which you write, like everything hard-coded is a literal. Okay, and right here, our literal expression can be any number, and any number is 42 and 10. But again, what kind of grammar is that, right? When we have like 42 and 10. So we will define our number in terms of another production rule. And technically, this will make the number a non-terminal symbol here. But I will still call it a terminal for all purposes. Well, because I'm going a bit ahead of myself, but whatever our lexer deals with, we will consider terminals. So anything it can process, any numbers, names, and things like that. But in any case, what is a number? It's a string of digits, right? And for an integer number, we can just have digits. And for a floating point number, we have a string of digits, potentially a dot somewhere, and a string of digits after the dot. So our number is our digit sequence. And we will define it like that. Okay. So what does this definition tell us about how do we recognize a digit sequence? Well, if we see a digit, we can say that what follows is probably a number. Like our digit sequence may be just one digit is a sequence, kind of. So we can have one digit or one digit and before it another digit sequence. So think of it like, well, it's a recursive definition, of course, but think of it like something which kind of starts with a single digit and ends with a single digit, if it makes sense. And anything in between are also an arbitrary number of digits. And well, if you look at this, you might wonder, like, the digit sequence is defined in terms, again, of a digit sequence there. So wouldn't it cause a problem with our grammar? Like, what if we try to recognize a sequence of digits here and we like go look, okay, that's a digit, so we need to like go look if it's a digit. I mean, what if we recurse indefinitely? If we just write some code which will use this rule and try to process our digits in like using this definition. But if you are wondering about that, we will address it later. Left recursion is not a big deal. It's kind of like forbidden in the grammar we are trying to make here, but it's not scary. Okay, and finally, we will define what digits are. And a digit is defined like that. So it's one of the 10 values from our input. If we see any character of this list, it's a digit. Okay, so let's kind of change our grammar here a little bit because, well, this sum rule thing, this one, what kind of name is that, right? And what does it do? And this plus here also, why is there? Shouldn't it be its own like a production rule? Because our non-terminal, it can contain raw input inside it, but usually it's good practice to avoid using this kind of raw input. Okay, let's start with a plus. What we are dealing with arithmetic expressions here with numbers, obviously. So what is a plus? It's an additive operation. And we have two of those. We have plus and a minus. So we can add or subtract, and this is an additive operation. So our sum rule thing will be called additive expression from now on. Additive expression is anything which has some expression on the left, an additive operation sign in between, and some other expression at the right. So let's look at it more closely. Right now, we only have literals, and we can only, our grammar only allows us to write code which consists of expressions of one expression, which says number plus number or number minus number. But that's not really helpful because in real world, when we're dealing with arithmetic, we can kind of chain operations together. So how do we describe that? So it's kind of easy to grasp the two operand binary operation thing in a vacuum. But how are we going to describe an arbitrary chain of operations? Like right here, I have three operands and two binaries chained together in a single expression. But we can have more. We can have like an infinite number of operands and an infinite number of operators plus or minus between them. Okay, so let's go ahead and define that. And this is how it's going to be defined. And you might notice that we have like literal expression appears twice here in this definition. So how should we read this? Any additive expression which consists, again, it's a binary of two operands and a sign between them. It might not be a binary expression really at all. In our case, it may be just a number. So if we write just 42 without pluses and minuses, this is what this is going to be a valid expression in our language. So we can just say 42, or we can say 42 plus 10. And at the moment we say 42 plus 10, the second line in this definition comes into play. So it can be either just a literal expression, or it can be an additive expression followed by an additive operator and followed by a literal expression. So one or the other. And here, this is where we get into this dreaded left recursion problem. Because like we have this expression 42 plus 10 plus 2, right? And we have a rule which says it can be a literal. Okay, let's take a look at this expression. So we have a 42, which is a literal, but then we have a plus. So this 42, it has to be not a literal expression, because our first definition of the additive expression does not allow for any additional tail, if you will, of this. So since we have something and then plus, this means that our second line, the second way to define the entire thing comes into play. And here, how we parse this from top to bottom is like that. So we have some input. We go inside and say, okay, so where do we start? Oh, our additive expression. This is our top level starting symbol. Okay, let's go inside and look. What's an additive expression? Oh, it's defined in terms of additive expression again. Okay, so what's an additive expression? It is defined in terms of additive expression, and we get an infinite recursion here. Technically, this grammar is not healthy, kind of, for our needs, but it doesn't really matter, because I will show you a bit later when we get to operation associativity and priority. So spoiler, this is not a big deal. I'm talking about it because it's confusing, okay? Let's, for now, just accept that we have this definition of an additive expression and look at this literal thing again. Right now, we can only kind of manipulate numbers, but what if we want to add variables? What if we want to add some kind of other expressions, like unary expressions? Right now we have 42. What if I want to do minus 42 plus 10? So instead of this literal thing, we'll create another rule and call it a primary expression, and it will be defined in terms of literals, any variable names which we will have eventually, parentheses expressions, and all those things which you can plus together, kind of. Well, in this case, in case of an additive expression. We will expand. Right now, our primary expression will be defined as just a literal, but we will expand it as we go. And like at the beginning, I showed this tree structure of a binary where we had left operand, right operand, and a plus sign. But what happens when we have more than two operands? Well, this here is a weird construct, really, if you think about it. Like an expression that consists of like 3 operands. If we look at it using the same approach, if we represent it as a tree, this is what we are going to get. Operations, arithmetic operations are left associative. We call them left associative. What this means is that when you have a chain of similar operations between a lot of different operands, what you do, you accumulate as much as you can in the left operand, then look at the operator, and then what's left after you accumulate as much as you can as the left one, it will become the right operand of your tree representation. Okay, so, and this is actually what this grammar is telling us to do. The way it is processed really is we look at it. So let's say we are a parser of our language and we are using our grammar. So we go, we take an input and we go look, what's the starting symbol? Okay, so the starting symbol is, in our case, additive expression. Okay, so what do we have here? Well, we have a primary, this one, if you see the mouse, I don't know. Okay, but anyway, we have a primary. So as a primary, we have a 42. And then if we have a plus sign, that means that we are still in this additive expression thing. And we take the second operand after this plus sign. And that's our left operand of a bigger kind of expression. This may be like a bit confusing right now, but when we go and write a parser, I will show you exactly how it's handled. Basically, we will have a loop which will run while we have the operation of the required rank or precedence before us. And then once we are out of it, we will go and do other stuff. Okay, so this is a left associative tree, which represents kind of a chain of similar operations. But what if we have different operations which need to be calculated in different order? So let's take a look at operation priority and how it works. Okay. So let's say we have now multiplication. And we have this grammar which says like additive expression is whatever we've been doing before. And this multiplication thing, this multiplication operator, it doesn't fit into our scheme of this left associative tree kind of. Because what we have to get in this case is our left operand is 42 and our right operand is this multiplication thing, the entire thing. So we somehow need to define this multiplication thing. And we are going to call it, well, you guessed it, multiplicative expression, because we had an additive before. So before, our additive expression was defined as a primary primary or additive plus minus primary. And now instead of primary, we have a multiplicative expression. And our primary will move into this multiplicative expression definition. And of course, we'll have a multiplicative operator, which is multiply or divide. And you might see a pattern here, right? So additive expression and multiplicative expression, they are defined in the same way, according to the same basic principle. They have the same structure. They just have different parts of them. And this is really the way the grammar is defined in a whole. So when you define a grammar, you start from the top and you say, okay, so to kind of define our language, we will say that we have a program which will be, let's say, an expression. And then you go and define an expression. You will say expression is this and this and that. And then you define this and this and that and so on and so forth. And it trickles down until you kind of bump into digits, numbers, and letters, and all those basic characters which you might get as input. So it's a huge tree with whose root is in the starting symbol from our grammar. Then this starting symbol branches into different non-terminals defined in terms of one another. And it ends at the leaves at terminals, which are not defined in terms of other symbols or productions. And for this multiplicative expression, our tree will look like that. So when we have like addition, 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 we had a tree growing to the left. Here we will have really quite a branch tree in some cases, depending on how many of those we mix together. But what you can see here is what I said when we just began with that multiplication thing. So you have a plus expression, which has the lowest priority. You have its operand, which is like just a number as a left operand, and you have a multiplication as its right operand. And multiplication has a higher priority than addition. And this operation priority, if we step back and look at that, it is actually written like right into the grammar. The way we process our input according to those rules is dictates what kinds of operations on what levels of the resulting tree which we will get will be there. So the highest priority things go all the way to the bottom, and the lower and lower the priority of some operation gets, the higher in the tree it's going to be. So it's kind of backwards. So you go, if you think of priority, you would think that the highest priority things go first, but really that's the opposite thing here. They go last in terms of their definition and their position in the tree, which we will get at the end when we are done with parsing. Okay, and so right now in our grammar here, we have addition, we have multiplication, but when we write arithmetic operations, like in real life, and we want to do it in programming languages, we can manipulate kind of this operation order by using parentheses. So before, when we did not have those parentheses here, we had this additive expression at the top, and it had 42 and a multiplication. But now we do have parentheses. And so what's written here, it's going to be a multiplicative expression at the top, and its left operand will be this addition, because parentheses change operation priority. And remember, whatever is has higher priority goes lower in the tree. So right now our multiplication kind of boop and went up as the top operation of the entire thing. And the way it is handled is related to this, to the primary expression. Why in the first place we added it at all in our grammar? Well, because we want to take like those atomic things which we treat as a single part of a bigger expression, and we want them to categorize in their own bubble, so to speak. So our primary expression used to be defined as just a literal, but now it will be either a literal or a parentheses. And if we look at this parent expression, it has an opening parenthesis, an additive expression inside, and a closing parenthesis. But really, why do we have this additive expression here at all? Well, we started from it. Currently, it's our starting symbol. But if we add things to our grammar, add different kinds of expressions and so on and so forth, and some of them might be at the same level with the additive expression, kind of like we have their literal, parent, and so on. So let's call this thing just an expression. Okay. So what we have here? Well, we have primary expression, which is a literal or paren. In parens expression, we have two parentheses and an expression inside. We will define what expression is momentarily. And we also can add a unary expression here. So we can say -2, right? Or +1. Because those pluses or minuses, they are not a part of the literal. So when you, and you kind of have to do it like that. When you see in some code like -1, it expands into a unary expression which has one operand of 1 and an operator which says minus. So our unary is going to be either anything our primary expression is. So we can just say 2 or 42, whatever. Or it can be a unary operation, which is again plus or minus right now. followed by another unary expression, not a primary. And the way it works, if you write like minus, minus, minus 2, what you will get? You will get a unary expression minus, whose operand will be a unary expression, again, minus, whose operand in turn will be a unary expression of minus, and the operand of that last expression will be 2. And when you kind of don't want to insert your minuses into your numeric literals, well, because, well, first of all, we will be expanding our primary expression and adding more and more things into it, different things. And it also kind of complicates the definition of numerics. And the third reason why you don't want your minus in your numeric things is it might create ambiguity, where you will have in your grammar 2 things that start with the same prefix. And that is really a bad situation if you have that in your grammar. Like, for example, in C++, we have this dreaded thing commonly known as most vexing parse, which makes it quite impossible to distinguish between variable declarations and function declarations, because both variable and function declarations start with a type name and a declarator. And then function declarations, of course, follow by an open parenthesis. But guess what? Variable declarations can also be followed by an opening parenthesis, because you can write initializers in parentheses. And so it creates a whole host of issues. And that's why C++ is very difficult to create a parser for, because it has such things in its grammar. So we don't want that. No 2 production rules in our grammar will start with the same thing ever. Okay, so let's take a look at whatever we have so far in this specific grammar definition. So we've got our digits, we've got our different kinds of, I'm on PowerPoint, you can do that. Different kinds of operators. And our digits can be combined into sequences, which mean numbers. And our numbers are literal expressions, and literal and paren expressions combined into primary expressions. We also have unaries, and we have additive and multiplicative kind of expressions. And looking at it, in multiplicative, we should have a unary instead of primary. So, yeah, this is not entirely correct, but I will spoiler you for you the real grammar in a moment, so no big deal. And we will define expression as a whole as an additive for now, and our entire program will be expression. So, okay, the way we are going to deal with that when we create a parser, what will happen? So program is our starting symbol. And this is where our parser will begin. So we feed some input into the parser, and it goes and calls a function which is called program. So those production rules, they are going to be kind of functions inside the parser. Functions will be called all that. So yeah, the program will call expression, which will call additive, and so on and so forth. And the parser goes from the top, from the the starting symbol from the topmost production, and it goes down, 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 down. Eventually, it reaches the lowest thing possible, which in this case is a literal. And then it goes up, 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 and it kind of collects on the way up, on the way back, bits and pieces of the entire program, and then they come together. This method is called a recursive descent, which we are going to be using for the parser. So you go from the top of the grammar, this kind of tree, and you go all the way to the bottom, and on the way back, you collect things back together. And why we are going to be using recursive descent? Well, because there are different kinds of parsers, different methods, and different algorithms, and some of them are kind of more robust than others, and recursive descent is not the best one in terms of correctness and maybe even performance. But it has one key advantage. Recursive descent, you can like just code manually. Other methods of parsing require state machines and some kind of generated tables for those state machines. And recursive descent, as a result of that, it is also the most flexible thing. You can code it manually. It's quite easier than anything else to debug. And you can customize it like really well. So you can cut corners. In some cases, you don't have to go absolutely by the letter of the grammar. So you probably should go by the letter of the grammar, but it's not kind of obligatory. Yeah, so since our goal here is create some usable interpreter kind of thing, our own small programming language, it would be fair if we use it like in an honest way, without using generators or any like helpers. We'll just code everything. Okay, and now with this presentation we've done, but I will give you a spoiler. What I have here, this is our language. You see I've got a project here, but it doesn't really matter right now. This is the grammar we'll be aiming for. And as you can see, it's kind of a big one, but not really, but it looks kind of big. So let's see what we've got. So in our program, yes, and for those of you who didn't see the last thing we did like a month ago, this is what we are aiming for. So this is factorial implementation in our language here. Two implementations, in fact, one recursive and one with a loop. So what we will have, our starting symbol is a program, which is going to be a list of declarations. And the same thing as with the digit sequence, same thing as with any other kind of list, is our declaration list can be either a single declaration or a list which ends with a single declaration again. And our single declaration will be either just an empty declaration, which you also have like in C++, where you can, at the top level, you can just type your semicolon, like any number of semicolons you want, and that's okay. Just a bunch of empty declarations. We will have variables. And if you see here, like you'll notice that we have variable declaration followed by a semicolon. So when we declare a variable, we will have to end it with a semicolon. But for functions, we don't have to do that. And that's also in languages which require those separators, like semicolons between different things. When your function has this body with curlies, for example, you don't have to terminate it with a semicolon, whatever. Okay, so variables. We will have variables. We will have types in our language. Variables will be like auto in C++ or var in, I guess, C# and Java. In terms of when you declare a variable, we will only have one keyword, like var, for declarations, but you give it a name and you have to initialize it. And when you initialize it, the type of this variable will be determined from whatever is in the initializer. So we will have variables with, what do you call it, with inferred types from their initializers. We'll also have functions. Functions will look like that. So you have, if you look here, you have fn, name, params, return type, which is optional, and a compound statement, which is the function body. And if you look here, this is the fn keyword, name, parameters, return type, which is present here, but you don't have to specify it. And this is our compound statement. The entire thing in curly. Return type can be empty or type name or just void. Params is yet another list. In this case, it's a comma-separated list, and so on and so forth. So parameters, we will have to declare them with types, because otherwise we will get into a meta programming template nightmare of, well, you don't want to go there just yet, of C++, when you can have auto here and it creates a bunch of, it creates template function for you, and then you call it, you will get a bunch of variations of that. We don't want that here, so we'll have just static types. We will have types int, float, and bool. Nothing fancy, nothing user-defined, but since our language is kind of, it's really simplistic, that will be enough for us. And yeah, compound statement is statement in curly's. Statement list is either empty or a statement, or the way lists are defined. And our statement can be empty. We can declare variables inside functions. That's an important thing, that statements can only occur inside function bodies. So you can have statements here on this level, only declarations. But here you can have statements. And you can declare variables, but not functions, which is reflected here. So We can have variable declarations. We can have just simple expressions followed by semicolon. Nested compound statements, returns. We will also have conditionals in the form of ifs, and we will have a while loop in our language. And return, of course, can be either just return with an empty thing which is returned, in which case it's void, or we can return the result of an expression. So that's the familiar stuff. Many languages have that. Okay, we will have ifs with an else clause. So we'll have if else, and we will be able to do it like this. This definition allows us to write like in C++ or JavaScript or whatever um, conditional statements like if something, else if something, else if something, else if something else, we're done. So else is of course optional. Okay, so we have whiles. And in expressions, this is what we've been looking at. In the presentation, I had additive and multiplicative kind of expressions and unaries and primaries, but here we will have logical or, logical and, different things which compare values like equals, less, greater, multiplications, unaries. We'll be able to call functions and a bunch of stuff. And like if you look here, all the binary expressions are kind of created equal. They all look the same. And I will show you how to avoid like duplicating code and writing things for every last one of them, because they are really just the same thing over and over with different. The only difference is here and here and here. So writing them all by hand is not a good approach in a parser. But anyway, we'll look at that. Okay, so we will have something called a postfix expression. Like in unaries, instead of primaries, we will have postfix, and we'll need it because we will have function calls, which we will be covering when we could get to functions. Okay, so yeah, this is the arguments. Yet another list, which is built in exactly the same way as other lists. Here's our primary expression, which depends on defined in terms of parent and literal. So parent. We'll have IDs, ID expression to reference variables and functions by name. And our literals will have integers, floating point numbers, true and false. Okay, so, and here, like starting from here, it's the low level stuff, which our lexer is going to handle. So this is basically our last non-terminal, the literal expression. In terms of, like as I said, this is technically a non-terminal, but for all intents and purposes, I will consider it a terminal symbol name, or where do I have the int number, float number? Those I will consider terminal symbols. Our parser will for sure consider them to be terminal symbols. And here you have it. The last thing, the lowest leaf, is going to be our digit and characters. By the way, this is just for brevity. These two rules I will explain them when we get to identifiers. Our identifiers will be allowed to start with a letter or an underscore, and inside our identifiers, we will allow having letters, underscores, and digits, basically. Okay, so any questions? Let's see something in the chat. Just a moment. Oh, Stefan, how important is knowledge of parsing theory, bottom-up parsers in programming language design, given that most languages seem to be implementable with a recursive descent parser? Well, I would say that I think most languages are implemented with recursive descent, because even C++, even though its grammar is terrible for recursive descent. Well, I would say that understanding that there are different kinds of things, different types of parsers can be kind of useful, but it's not like really, really critical. Because you can get away with recursive descent in most situations. And if you want to do something which is not recursive descent, you will have to probably feed your grammar to something like what's it called? Bison, Yak generators, which will build for you a state machine based on your grammar. Because you could do it like manually, but that would be a nightmare. So I would say, yeah, for understanding, to broaden your view kind of on the things, knowing it is useful, but for practical implementations, recursive descent is your dude. Like you can't go wrong with with it, really. No, I hope it kind of answers your question. Um, well, oh, by the way, I hear sometimes from people like, why write things manually? Like, why don't you just generate things with generators? Well, because if you use a generator, then you didn't really build your thing yourself, but that's not a really big deal. More importantly is that you kind of lose that level of control and customizability, if it's a word. So if you have generated a parser, it will be more difficult. It will be like a black box for you, if it makes sense. So writing one by hand, even if you are not planning to ever do it after that, I guess it's a useful thing. Okay, so any more questions from anyone? All right, so yeah, I guess that's it then. And thank you for coming. Our next thing is gonna be a lexer implementation. And the way it's going to go is I've not decided yet how we should organize it, really. Whether I would kind of create a new project and build it from the ground up, or which will take a lot of screen time here if we do that, or kind of I will just show you already implemented code and explain it. probably I will go with the implemented code because just because you don't really want to see me like sitting here typing all day. Oh, okay. And yeah, I guess thank you all for coming, and we will end here. So goodbye.